Recording, it says. So we had the test. We're moving on, and now we're going to spend one chapter talking about math, and then we'll get back to quantum mechanics. So the reason we have this is because, well, as our textbook says, the wave functions exist in Hilbert space. When I was in graduate school, we said that Dr. Park lived in Hilbert space because he seemed to us to be the kind of person who could actually understand this stuff, which to us mere mortals, it seemed like a whole lot of what, why, huh? So first thing we want to do is to make sure we understand what things mean. So start off with this here. Now I've already talked about the Brockhead or Dirac notation, but this here, not in a pen mode, this here is what we've been saying, okay, that's our wave function, psi of x. That's, of course, the time-independent wave function. And then we say here, using the Dirac notation, that's equal to bra x ket psi. And at this point, it already seems just a little bizarre to say like bra ket x or bra x ket psi is equal to psi. We will, for the most part, just write this here and say we good. Because your wave function can be in terms of different variables. Right? You can have the wave function in terms of x. We didn't do this, but we could also have made our wave function, for instance, in terms of momentum. And so if you put psi, that means your wave, ket psi, ket because it's the second half of a bracket, bra is the first half, ket is the second half. Then that is your wave function, and you could put it in any variable space you want with a bra. And then a meaning here, bra, I should have put, instead of psi, maybe I should have put, well, I'll put psi 1 and psi 2 is equal to psi 1 star psi 2 integrated over all space. So when we close the bracket, it implies an integral over all space. If you look in the textbook, it says over an interval and puts a and b as the limits. But we are going to just simply put minus infinity and plus infinity because generally our space is infinite. We might be constrained like particle in box where it was 0 from minus infinity to 0 and 0 from a to infinity. I'm sorry, I sneezed. I've been trying to fight it, which is why I've been sounding funny here. I think it's gone away. Notice something important. When it's in the bra, it's complex conjugate. That star means complex conjugate. So remember, that means anything with an I becomes minus I. Now, linear algebra is what Appendix A 1 and 2 is about. So we're going to do some linear algebra ideas here along with understanding this Hilbert space. So our quantum theory is based on wave functions and operators. The wave function, I think you had this in the first test, it tells you all the information. And the operator, well, what's the purpose of an operator? It extracts the information from the wave function. And mathematically, a wave function satisfies the conditions for a vector. An operator satisfies the conditions for a linear transformation or a matrix. So wave functions are vectors. Now, if you had a finite space and whatnot, it would probably be pretty easy to think about that way. But with an infinite space, with an infinite number of dimensions, and so on, it becomes hard to think about these functions of x as being vectors. Now, our textbook, I did not put this in my slides, and I should have. Our textbook adds a definition here that, and I want to make sure that I make it the same exactly as the textbook so that you don't say, it looks similar, but it's not the same. What did he do different? Was he right? We'll just make sure. Okay, so it uses alpha. I want to make it look the same. How would you say this? I mean, what do I have written there? Well, this here has a name that goes with it.
Ket.
Yes, you say ket alpha, right? Just so we can speak and understand what each other are saying. So ket alpha it has a bold A. I put an A with a vector sign over it. So ket alpha is representing vector A, which a vector in linear algebra formulation is in this those are all A's, by the way. The last one looks like a 9. Is an n-dimensional it's a one-dimensional vector of what we say rank n. It has n elements in it. I don't have the right mathematical terminology to get that right, but it's a one-dimensional array. That's what a vector is. And so when we write this ket alpha, that's what it represents. And if we do a bra alpha, it's actually a little more than A star. I'm just going to go right to what it actually is and not put that because it will confuse us even worse. What's different do you suppose it makes if I go from the ket to the bra? I'm asking you, I'm not expecting you to necessarily be correct. So don't feel bad if you don't get it right.
A row instead of a column.
It's a row instead of a column is the correct answer. So this is going to be, and I'm going to write it incorrectly at first. Does anybody know what I wrote incorrectly? Nope. Bra becomes complex conjugated.
Oh, okay. So you didn't want to put the A vector. You didn't want to put an asterisk by it.
Right. 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 It's transform. There is a way of writing it, but I just didn't want to confuse it. It's not shown here in the textbook in this regard, so I just figured let's not cause a problem. Now, what do I get when I put that together? Actually, it goes the other way. I will show you that one because there is that option as well, but it's the opposite order. If I do ket bra, it becomes a matrix. If I do bra ket, it collapses to a number that you get by taking what we just wrote I didn't want to put more than 3 elements. So how are we at our linear algebra, our multiplication of a row vector by a column vector? Not? Okay. Being honest is best because then I know what we need to do. With linear algebra, when you multiply vectors or matrices, because a vector is just a special case of a matrix, you take first all of the items in the top row and multiply them by all of the items in the first column. So the number of rows in the first one must equal the number of columns in the second one. Otherwise, you can't multiply them. So when I do this, I'm going to have A1 star A1, first one times first one. And then I go to the second element in each one, plus A2 star A2, plus dot, 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 plus an star an. Or using something that this is now moving away from drawing out the vectors, equals the sum over n of an star an. And actually, I did not do that right. I should have used I equals 1 to n, like that. So that's just the math of how this plays out. If alpha was a solution to the Schrodinger equation that's been correctly normalized, what is this going to turn out to be?
The integral of psi star psi.
Okay, that is correct, but what is the number going to be? 1. If it's correctly normalized, that needs to come to 1, because it was alpha with alpha. And if it was like alpha with beta, which was not alpha, yeah, if they're eigenstates, individual eigenstates, which, once again, that brings up the eigenstates, steady states, whatever you want to call them. One last thing I should mention here before I move on. You guys probably never heard of Einstein sums, have you? It's just something to be lazy. And you know what? We like to be lazy. What I have written here is identical in meaning to that. And you look at this and you say, how is that identical in meaning? It's an implied summation. If I have the same index in two items, it implies I'm summing over all values that it has. So we have these implied sums that we have to be aware of as we go through and look at linear algebra things. So I've covered quite a bit on my opening slide here. But it's all the nomenclature and how the math is written that we're dealing with. So are there any questions about what I've done on this opening slide? Because, if there are, I need to address them. Okay, so we've already talked about this slide, properties that vectors have. So here, to get us comfortable, we're using kets for each of our vectors. And when you see that ket alpha, you're thinking, that's a column vector. And if I saw bra alpha, that would be a row vector. And so if I have alpha plus beta, that should be the same as beta plus alpha. That's called the commutative property. Basically, it doesn't matter what the order is when you're adding. Then we have the associative, alpha plus beta plus gamma. It doesn't matter what the order is for addition, you're going to get the same thing. And finally, distributive property, if I have a constant times alpha plus beta, that constant can be distributed to each thing inside. So that's the constant times alpha plus the constant times beta. Those should not be startling or confusing, right? Those are things that you're familiar with. There are things that we see with all of our math that we're used to using, but not in all math. Now, the definition of Hilbert space. A Hilbert space has to be a complete inner product space. If that made sense to you, you're way overeducated on the math side for this class. A complete inner product space. Complete, I know we actually might have had this on a test. I remember Chad coming and saying, what is this complete? What does it mean? And so complete means that you have all of the possible directions that are mutually orthogonal, so that any vector can be written as a linear sum of each one of your states. So here we have psi, a vector, ket psi, to be accurate, is equal to the sum of a subscript j, which is just some constant, multiplied by eigenstate J. Once again, I'm using that term eigenstate. Eigensystem, you have different levels, and each level corresponds to an energy. So I take some constant times state 1 plus some constant times state 2 plus some constant times state 3, and I should be able to make any function by doing that. That's what it means for it to be complete. Now that didn't say anything about the inner product space, just that it's complete. So what is an inner product space? An inner product is, I would say, another name for it, but it's a more nuanced name, a more complete name for what we think of as a dot product. So, especially if you've taken physics from me, you've learned that a dot product is multiplying the parallel parts of vectors. So, the inner product is indicated with bra alpha ket beta. That's the inner product between alpha and beta. And as we've just seen, when we close the bracket, that has an implied integral. And so the inner product is the integral over all space. Our textbook says on an interval A to B, and I'm just going ahead and making that all space. The bra is complex conjugate, the ket. And so now you look at this, you say, well, I mean, technically I can write that down for any set of vectors, right? So what's so special? What makes it inner product space? It's inner product space if this integral is always less than or equal, or it's not less than or equal, less than infinity. If that integral goes to infinity, it's not part of the inner product space. So this here has to be less than infinite. So what is a Hilbert space? A Hilbert space is the set of all square integral functions on an interval. An inner product is square integral. This is math. As far as a physicist goes, this is math mumbo jumbo, right? We look at it, we squint our eyes, and then we try to make reality out of it. If you're a mathematician, this is some serious stuff. Our textbook says to mathematicians, there's a special name for this. It is, technically, a Hilbert space is a complete inner product space. I think I said that. Yeah, here. Mathematicians call it L subscript 2, parenthesis, A comma B, where A and B are the interval limits, which I've been using minus infinity to plus infinity. So that's the mathematical terminology. And believe me, really important to some people. To we physicists, we call it a Hilbert space. We understand the completeness idea is very important. The fact that you have to be able to do an inner product is very important. So those are important things, and then we go on. Ready to go on, or you want to talk about some more?
We just find that it's complete from making it orthonormal, right?
If you can show that your solutions are orthonormal, then it is an inner product space. It doesn't necessarily show that it's complete, just that they're orthonormal. I'm not remembering how to show that it's complete, how to show that you can make all vectors. I'm pretty sure there's a way, but I can't think of it offhand. But that's the rubber meets the road. That's what we need to be able to do in physics, is understand the ideas of orthonormal, right? If it's orthonormal, then you've fulfilled that requirement, right? Because we use normalization constants to make it equal to 1 or 0. Now, Hermitian operators. Sometimes I wonder at all the jargon that I've learned in life, and if I just throw it out way too quickly, because I've had Hermitian all my life, and like many of the things here, I've never been really strong on the fundamentals of it. Just, well, it's a thing. So, first of all, Hermitian operators are operators that are going to produce a real eigenvalue. That is, we know that operators extract the real or the observables. And observables are real things, right? You don't say, oh yes, this has a mass of 35 I grams. Right? You don't have a complex mass. It's a real value. Same thing with energy. You don't have a complex energy. It's real. And so because our expectation values need to be real, then we are set with a restriction. This is how you find the expectation value, right? And if you take the complex conjugate of the expectation value, it should be no different because it's real. So the expectation value should be this or this, but this here is the same as this. And so this actually puts a rule for our Hermitian operators. And I'm just going to jump to doing a homework problem with the definition for Hermitian operator so we can get the feel for this. One thing to note here is a Hermitian conjugate, also known as the adjoint, so sometimes you'll say adjoint, is written as Q dagger. Right? So if Q is my operator, Q daggers, it's Hermitian adjoint or Hermitian conjugate. Not the same thing as a complex conjugate, at least in terminology. We're going to do a problem to see how it comes out. So, problem 3.5. If you look in your textbook, let's see where problem 3.5 is. Problem 3.5 on page 98. It says the Hermitian well, I think I wrote it out here, is defined with this function that I put. So, bra F ket Q operator G is equal to bra Q operator adjoint FG. And then we have A, find the Hermitian conjugate for 3 different things, and B, show that QR's combined adjoint is R adjoint Q adjoint. Guys ready to tackle this? Chad nods his head. That's just a sign of courage, isn't it, Chad? Sure. So let's start with this. What does that translate to if we write it out as a function? Or what is that shorthand for?
The integral of F star times the operator times G.
And, you know, I'm going to change colors here so I can color code a little bit. Whoops. I mean, I wrote everything right, but I forgot to change the color of this. Okay, so that's what that translates out to. What about then once again, nice color coding. What does that translate into? Now notice I didn't show my limits. My limit should be overall space, so it should be minus infinity to plus infinity. I'm being a little lazy, so just make sure you're aware of that these do have set limits. What does it translate to?
So is the Q operator now acting on F star instead of G?
Almost. It is, but it's not Q operator dagger. What is it? Because it's in the bra.
I said Q star.
Oh, you did say Q star. Mm-hmm. Okay, I didn't hear that. So yeah, it's going to be Q dagger star operating on F. And then G dx. So our definition up there says that these two have to equal each other. And we're going to use that to find what Q dagger is.
So why don't we have F star anymore?
We should. I did not write that for reasons that can only be considered as, what's that word when you can't remember stuff? Just like the same reason that turned out to be blue instead of black. Yes, forgetfulness. Okay, so now we can get to work. So I'm just going to take what is this first form. So let's call this one here A, or A is bad. Let's just call this the first form. Let's do the first form for X and then match it up against the second form. So for X, I would have now X. What can I do with this now that I put my X operator in? My X operator is just X, so
you can move it.
I can move it freely within the integral. So that's the same as, whoops, integral X F star G dx. And now by inspection, I can make the identification, didn't mean double click, that Q, well, in this case, the Q was X, right? So X operator dagger star is equal to X. So how do I find X dagger, X operator dagger, if I have X operator dagger star? You do what?
You're asking how to find X operator dagger.
How do I get rid of this star? That's what I'm asking.
Take the complex.
Take the complex conjugate of both sides. So I'm just going to take the complex conjugate of both sides. And so I have X operator dagger equals, what's the complex conjugate of X? Position is a real value. And so what is that equal to? Right. So there we found the Hermitian adjoint of the X operator is still just X. Lest you feel like this is going to be too simple, they're not all going to turn out that way, clearly. So now we're going to go to I. Integral of F star I G dx equals, okay, so I is, it's complex, but it's just a number. We can move it around. We can move it outside the integral if we wanted to. I don't want to move it outside the integral, but we could. So I'm just going to rearrange this to, is the integral of I F star, remembered the star this time, thankfully, G dx. Now, once again, we're going to compare that to form 2. And we immediately get an answer about what Q, in this case, the I operator, dagger star is. So we're going to have I operator dagger star equals, and what do we have there in that position? in the position of the Q dagger star, what do we have? What did you say, Chad? Just said I. That's right. And then using the same step to get to just the I dagger, I do the complex conjugate of both sides.
I don't know how you got that.
Okay, so I took this position here. What's filling that position? And it was this.
How can you compare the second form to the first?
Because that's the definition of Hermitian conjugate. Hermitian conjugate says the two have to equal. So that's what our test is. So I have I dagger star is equal to I, so I'm going to take the complex conjugate of both sides. And I get then that the Hermitian conjugate of I, what's I star? Yeah. And in retrospect, that's not very surprising either. What we've done so far is we've just taken the complex conjugate in both cases. And so now you start to feel like, hey, maybe the Hermitian conjugate is just a complex conjugate. I know someone who used to believe that too. So we have a third case to show that that's not true. So our third case, whole out of space. I'll add another page rather than trying to be some smart aleck. Guess we're not going to do it, you know. So our third case, we're now going to use ddx. And of course, at this point, you're like, this is what they put on the test, right? They put the first two to get you warmed up in homework. Now on the test, they put the third one to make sure you understood it. Did you agree with that? So doing it for dx, the integral of f star ddx g dx equals, I can't move the ddx around like I could the others. So this is going to take a little more work. How can I approach it? And really, sometimes we do stupid stuff like this and make this the test question after we've given you the two law balls. And then, so what do we do here? How would you, okay, we don't know what f and g are. They're any possible functions. So how could you do anything with this to rearrange it? And this is a calculus question. Integration by parts. We integrate this bad boy by parts. So we let, I don't know why I'm so stuck on u and v. I mean, this is already perfectly in integration by parts formalism, right? But I have to. It's the way I was trained. So we let u equals f star and dv is equal to dg dx dx. And so that means that I'm going to have v is equal to integral dg dx dx is just going to be dg dx. Excuse me. Yeah. It's just going to be g. And in a similar vein, du is going to be equal to df star, well, we'll just put df star. And so if I do my integration by parts, this is going to be equal to that, right? So just substituting in, u is f star, v is g, minus integral, and then I'm going to have v, so I'm going to have g, and then I have and there I being complete. And I forgot to put my complex conjugate there, so get that in there. Now I have the derivative acting on the f star and no derivative acting on the g. I can rearrange the positions of these without a problem. I couldn't move my derivative around, but I could have, for instance, I could have taken this and said that's equal to dg dx times f star in my original integral. That would not have been a problem mathematically. Right? Function A times function B is equal to function B times function A. It was having the operator that we couldn't move. So I can rewrite this now. This first evaluation, what can you tell me about the value of f and or g at x equals plus or minus infinity? Must be 0 for it to be square integrable. For it to be square integrable, for us to have our inner product, those have to be 0. So I can right away just put that as 0 because it's 0 at both of those limits. It's 0 times 0 at both of the limits if you want to be really technical. So what I'm left with is minus integral d dx of f star I better put that derivative is only of f star. I'm going to bring that minus sign inside right there. Why did I do that? So I can see, and this time I have d dx was my operator. Our equals, and what I have from reading off, comparing to that position that has the cyan box around it. What do I have operate or acting on f star? So the complex conjugate of the adjoint of d dx is minus d dx. So now I want to get rid of the complex conjugate. So I do the complex conjugate on both sides. And I have the adjoint of d dx is equal to, what's the complex conjugate of d dx? Since x is real, it is, yep, still d dx. Don't forget the minus sign that was out front. So there's our Hermitian adjoint of d dx. And so in this case, there was no complex values. There was no I, but we changed the sign, which shows you that it didn't follow the simple rule you might have surmised from the first two examples we did. So I think I gave you a homework problem or two to check and see if something's Hermitian. How do you check to see if something is Hermitian? That's right. You check and make sure that this first equation is true, which is what we just did. And so this process is how you would check. We found the adjoints, but if we're going to show that it's Hermitian, we have to go through and make sure that's the case. There is a last step here. Show that the adjoint of QR is equal to R adjoint Q adjoint. I'm guessing you don't have an idea how to do that, right? I mean, that's the reason I bring it out and do the problem, is to make sure that we understand how to do some of these things that turn out to be really important. It's really important that you remember that if it's in the bra, it's the complex conjugate. A big reason why I've been doing this in the long form is so you see, yes, it's complex conjugate for the bra part. So if we had Q dagger, it's actually Q dagger star if it's in the bra. So I'm going to take this and I'm going to write it out in so I have actually, yeah. Let's start it a different way. Start it a different way. I'm going to do that. Now I'm going to turn to the next page, but that's what I'm going to start with. Actually, I'm going to add another page. It sounds crazy, like how much more lecture does he have? This is my last page of the lecture. Nothing more. I did expect that this would take a full class period. So what we want to show is that and so what I'm going to do is alpha QR beta. So by rule, this should be equal to QR dagger alpha beta. Right, I took the Hermitian adjoint when I moved it from the ket to the bra. That may not have been clear when we had it, but that's what the rule was. If you move it from the ket to the bra, it's going to become adjoint. So that's one way of doing it, but there's another way of doing it. Another way would be to use the properties we've seen of our, of our vectors, that this is the same as yeah. We often actually put a line here, but of R acting on beta. So Q is acting on R beta. Do you understand what I wrote there as far as what it means?
I don't understand how you're doing the parentheses.
Okay. Then let's move away from using the Dirac notation to doing the full notation. So this would be integral of alpha star Q R beta dx, right? That's the first form. And then I'm just saying, so R is acting on beta, Q is acting on R beta. So I'm just saying Q is acting on the combination of R beta. So I'd have R act on beta, and then after I have R act on beta, then I do Q acting on R. Well, Q acting on the result. But if I have it like that, then I can say that's equal to Q adjoint, and remember I got to do a star if I'm writing it out in integral form. Or as I was going to write here, so I'm going to take away the operator little hat because it's the only place I've used on this entire page. So these two lines are the same thing, one written in the calculus form and one written in our bracket drag notation. But you probably can see where I'm going now. I've moved the Q across because Q is acting on the entirety of what follows. Now R is acting on the entirety of what follows, and I can bring the R across. But just like the Q went to the first position, now the R is going to have to go to the first position. And so if I go one step further on this, so I bring this R over and making it the adjoint. So I have R adjoint acting on Q adjoint acting on alpha, beta. So you understand why we brought them over one by one, and it had the net result of me changing the order from QR to RQ. And so by definition, this right here is the adjoint of what we started with. Right, what we started with in this position here, we now have the adjoint in the front position. And so what we've shown is that QR adjoint is equal to R adjoint, Q adjoint. And when I say adjoint, it's Hermitian adjoint each time. You guys are feeling really good about this, aren't you? Yeah, not quite. If you were, I'd be wow. You know, like I said, you're way too mathematically prepared if this stuff is all, yeah. Boom, got it. Any questions to vocalize at this point in time?
Yeah, can you scroll back up?
It's a question. It's a question. It's not a conceptual question, but.
So on the last blue integral.
Yes, the only one.
Right. Why is an alpha?
Don't. You just had to show that not only Aaron can show when I made a mistake. Yes, that was a mistake on my part. I'm sorry. I know. I'm joking like you just had to show. No. Seeing an inconsistency and questioning why is it there, it may or may not be an error, right? It was an error, but it's good to ask.
Okay, so you only put the dagger in when you're moving it from the ket to the rod, right?
Well, you would if you moved it the other way as well.
Okay, so you call that the what now? The adjoint?
The Hermitian adjoint or the Hermitian conjugate. Either one works.
Okay.
See, we don't have to put those stars when we use the direct notation. All right, I don't think I have your homework visible to you yet, do I? So I've got a lot of jobs to do today, and that will be one of them, to get the homework visible so you can.
That's when we do Wednesday, is it?
Well, we have today and Tuesday's lectures before Wednesday. And so it's actually, that is the.
Usually you have it due a week after we have the lectures on something, or we have at least the week to work on it.
Well.
2 days to work on it.
Okay, so the time frame is different than what I was thinking. What I was thinking is, it's always Wednesday, Monday, Tuesday's lectures is what the homework is due on Wednesday is over. And so I never expect people to start until, Monday. But maybe that's just my poor expectations. I know you're a good student. You start before I've lectured over it.
I can't get it done in 2 days.
Well, okay, how about if I shift it so it's due, like, let's say Friday at 5?
Okay.
So it'll still be the same material, but giving you more time to do it to make up for not having the lead time to do it.
Yeah.
Okay. I don't want to cause a problem. I hate it when I go through the entire lecture